So motion, some physics, which should be useful to you in your studies of chemistry, kinetic theory, and what have you. So okay, so here we go. Motion. The contents of this, we're going to include the following things for you. Scalar and vector quantities. It's important that you know the difference between a scalar and a vector. We'll look at SI, Système International, SI units, speed, acceleration and momentum, potential and kinetic energy, and we'll also look at Newton's laws of motion, especially a really important one, F equals ma, force is mass times acceleration. Scalars and vectors. So a scalar property is fully described by its magnitude. In other words, it has size. A vector quantity, that's got size, magnitude, and direction. And it gives you a more complete description. Which are vector and which are scalar? So temperature, mass, pressure, velocity, speed, force, momentum, kinetic energy, and acceleration. They're all words that you'll hear. So I'll do this in a way that you can play along at home, all right? So temperature. Well, the answer is scalar. It's got just size. Mass. Scalar. Pressure. Force divided by area. Scalar. Velocity. Vector. And speed is scalar. That's the difference between velocity and speed. Force, newtons. Vector, well, it's up for sort of dispute. I mean, sometimes you don't need to be concerned about the direction of a force, but strictly speaking, it's a vector quantity. Momentum, it's mass times velocity, which should help you. Vector. Kinetic energy, the amount of energy an object has due to its motion. It's a scalar. Units are the joule. And acceleration is vector, rate of change of velocity. The base SI units for the following properties. These are the things that you have to use in formula, and therefore we should be giving it a bit of attention. So just to pick some quantities: speed, acceleration, force, linear momentum. Speed is meters per second, sometimes written as ms to the power minus 1. Acceleration, meters per second, or ms to the minus 2. Force, newtons, big N. Linear momentum, velocity and mass multiplied together, and so you get kilograms meters per second. Mass, more quantities, weight, kinetic energy and potential energy. Well, mass, kilograms. Weight is a force, newtons. Kinetic energy, joules. And potential energy, joules. Speed, it can be defined as the rate of change of position. You're moving something from here to here. Its position is changing at a certain rate. And the way a scientist or engineer or person might write that is that the position can be defined along a coordinate x, and its x is changing, its x value, its position is changing. And you write it as dx by dt. That's the nomenclature that's used. The rate of change of x with respect to time are the wordings for that. And the units of speed, m/s, or s to the minus 1. Remember that s to the power minus 1 is exactly the same as 1 over s. Okay? And m/s is really meaning meters divided by seconds, distance divided by time being speed. If you did a distance time graph, as we see down here, with distance on the y-axis, and in other words, the object is moving away from you, and you're saying, well, where is it? And you're asking the same question, how far away is it, say, every second? And you plot a graph of that, and you're saying, well, if it's moving away. And then you want to measure the gradient, which we're doing here. The change in the distance divided by the change in the time taken, okay, the change in time, change in distance over change in time is going to give you the speed. A little bit of calculus. If you had a curve instead of a straight line. In other words, if the distance that the object is moving is every second is changing, okay? In other words, sort of over the first second it moves a certain distance, but over the next second it's gone a bit further in the same amount of time, you'd end up with a curve. And that's very difficult. So how do you then start saying, well, what's the speed now? Well, you can't. You have to say, what's the instantaneous speed? What's the speed it's going at after 5 seconds, in my example? And the way that you would do it is you draw a line. This line here is called a tangent, and you take the gradient of the curve. Tangent is a straight line that only touches the curve at one point. And the slope of that tangent will tell you the instantaneous speed. Isaac Newton wasn't very happy with that, so he invented his own new type of mathematics, calculus. dx by dt, the rate of change of x with respect to time, tells you the speed. Okay, x is distance or position. The sort of derivation of calculus is wonderful. I think it's quite beautiful, brilliantly clever. What you have to imagine doing is drawing 2 points incredibly close together. And then the sort of gradient between these 2 points, where you're saying there's a little bit of time and there's a little bit of position change or a little bit of distance, dx by dt, and the points are so close together that when you do an intersection, you draw a line connecting, and what you've actually got is the tangent we were interested in the first place, dx by dt, and that gives you the speed. Now, acceleration is important as well. It's change in velocity divided by time taken. Rate of change of velocity, and its units are meters per second, or meters per second, ms to the minus 2. So velocity time, and on this graph here we're seeing that it's a straight line, so the velocity is changing linearly. It's changing every you go and look at the speedometer every second, and you're seeing that it's going up in equal intervals each time. Linear acceleration. In calculus notation, you would say that it's the rate of change of velocity, dv by dt. If you've seen some of the other bits and pieces on electrostatics, remember that big V is electrical potential and little v is usually used for velocity. Here, velocity, dv by dt, acceleration. The rate of change of velocity with respect to time. So this graph here is a distance time graph, and what you can see now is a curve. So what you can see is that over the equal time intervals, the distance that it travels in each equal time interval is not the same. It tells you that the object is accelerating. Now, the velocity would be written as dx by dt. We've just covered that, so it's the rate of change of distance, rate of change of how far away the thing is from you. We would call that dx by dt. It's called the first derivative. What it means is you have differentiated, done calculus, done this differentiation thing once. If you were to take that answer and do it again, you're said to have found the second derivative. If you're doing some maths modules with your course, you'll do this. And so this is really interesting. If you take a distance time graph like this one here, and you do differentiation on the function, you need the equation of the curve, and you differentiate it once, you end up with a sum that can tell you the velocity that the object is going after any time from the start. Which is quite a cool thing to be able to do. If you take the same mathematical function, you differentiate it once to give you the velocity function, and then you differentiate that once, so in other words you've differentiated twice, you end up with a little sum that can tell you its acceleration at any time since you said go. And you write that as d2x by dt squared. Okay, so that's acceleration, and it's called the second derivative of position with respect to time. If you want to know who cares, I'm not thinking about things moving around, I'm a chemist. If you go to your first kinetics lecture, they will almost certainly write d something by dt. And so you need to understand that it means it's the rate of change of a quantity with respect to time. You'll very often see things like this, d square bracket a by dt. That will give you a classic start to a rate equation. It means the rate of change of the concentration of a, whatever a is. Some really useful formula for you. V is u plus at, that's A-level maths. The final velocity is equal to the starting velocity plus the acceleration times the time. S is ut plus a half at squared, again a really useful formula. S is distance or displacement, u is the start velocity, time is t. A is acceleration, and if you're dropping things, it can be g, acceleration due to gravity. And the last one of the three, v squared equals u squared plus 2as. V final velocity, u starting velocity. Momentum, a slightly confusing concept for some people. It's not used a huge amount, I suppose, in sort of daily, day-to-day sort of speech. Momentum is mass times velocity. Those little Newton cradle things, which some people have on their desks, so you lift a little ball bearing on a wire and it moves in and the other one goes, and you get this sort of effect going. So the one here is just starting to, or is moving inwards, and so it has some momentum, mv. It's got mass and velocity. And this one here isn't going anywhere, so its v is 0. It's got no velocity, so its momentum is 0. So its mv is 0 here. mv is a value for that one. The units of momentum are kilograms meters per second. Momentum is conserved, really, really important principle in physics. And so all of the momentum has to be transferred from one of the little ball bearings into the other. And so one will come to a rest and the other one flies off with the same speed. Potential energy lost equals kinetic energy gained, GCSE science. If we have an object up high and we allow it to drop, well, okay, just before it drops, its potential energy is a maximum. And potential energy for objects waiting to fall is defined by a formula. It's their mass times the acceleration due to gravity times the height they are above where it is that they're going to fall down to. When it's mid-flight, it's got some potential energy because it's still got some distance left to go, and it's also got kinetic energy. It's gathering kinetic energy. And just before it hits the ground, or right just before it hits the ground, all of its potential energy has been converted to kinetic energy. And the formula for kinetic energy equals a half mv squared. And if you're feeling keen, you can work out a formula for v, which is really important. If you use a classic sort of question, I start with an object here. It's 50 centimeters above the desk. Its mass is this much, though you'll find that's irrelevant. What speed does it hit the bench? And you can just say PE lost equals KE gained. Put the two equations equal. Do some rearrangement and cancellation, and it's quite easy to do. Newton's law of motion. Isaac Newton, 1642 to 1727, if not the nicest man who's ever lived, perhaps one of the cleverest. His first law of motion. An object remains at rest or moves with a constant velocity in a straight line unless acted upon by a force. An external resultant force, if you really want all the words. This is the bit that is worth drawing to your attention. An object moves with a constant velocity in a straight line unless acted upon by a force. Okay, so if we don't think of things continuing to move forever, but they would if it wasn't for frictional forces like air resistance, for example. His second law of motion, the acceleration of an object is proportional to the force causing it. If you shove something really hard, it's going to accelerate faster than if you shove it gently. And his third law of motion, the action of a force produces a reaction in the object that is equal in magnitude but opposite in its direction to the action. In other words, if I push upwards on the table, then you can imagine the table meeting that downward force with an equal but opposite force. It's a way of working out problems like that. Newton's second law of motion. At school, you will have been asked to learn or become familiar with that force is mass times acceleration, F equals ma. Going a little bit beyond that, Newton's second law in fact tells us this. The rate of change of momentum, dmv, that's momentum, by dt, is proportional to, there's the proportionality sign, the force applied to the object. So dmv by dt is proportional to F. Just write it the other way around. You can get rid of a proportionality sign like this by adding a constant of proportionality. So we've done that here. F now equals k dmv by dt. The mass does not change. The mass of the object that we're accelerating, moving around, is constant. And so we can rewrite this because we don't need to talk about the rate of change of mass. We need to, which is here. This can be moved. That is going to change. We need to talk about the rate of change of velocity. You're moving, you're pushing something, it's going to accelerate. And so you can now write it like this. Force equals, you take the m out of the differential because it doesn't change, m dv by dt. And what you'll see is that m has become our constant. We needed a number that didn't change to put with an equal sign to get rid of this proportionality constant. So we've now got F equals m dv by dt. I've written down here 1 Newton is 1 kilogram meters per second squared. It's the force which would make 1 kilogram accelerate at a rate of 1 meter per second per second. I've just got this far. dv by dt, which you're seeing up here, is equal to acceleration, the rate of change of velocity. And so substitute dv by dt for a, and this equation here becomes this equation here that you learned at school, F equals ma. Two useful things. People are often confused between the difference between work and power. Work is the energy transformed. Remember, you don't create energy, you don't use up energy. The energy transformed to do something. And the formula that I do suggest you try and learn is that work is equal to the force applied times a distance travelled. Power, that's slightly different. It's the rate at which energy is transformed. So work is the energy change to do something, and power is all about how quickly does that change happen. Power is work done divided by the time taken. Work has got units of joules, it's an energy transformation, and power is joules per second, and that's got the unit watt, James Watt, okay, watts. Three little details. Please remember, weight's a force, and it has units of newtons. Mass is what you're really using in chemistry, grams, kilograms, okay? The SI unit, the base unit that you have to use in formulae for mass, is kilograms, not grams. And if you see the term negative acceleration, it means deceleration. The thing is slowing down. Thanks.